In this module, we shall learn about the special cases of linear programming. Linear programming is the process of taking various linear inequalities relating to some situation and finding the best value obtainable under those conditions. A typical example would be taking the limitations of materials and labor and then determining the best production levels for maximal profits under those conditions. In real life, linear programming is a part of a very important area of mathematics called optimization techniques. This field of study, or at least the applied result of it, are used every day in the organization and allocation of resources. These real-life systems can have dozens or hundreds of variables or more. In algebra though, you will only work with simple and graphicable two-variable linear case. The general process for solving linear programming exercises is to graph the inequalities called the constraints to form a walled area called the xy plane called the feasibility region. Then you figure out the coordinates of the corners of these feasibility region, that is, you find the intersection points of the various pairs of lines and test these corner points in the formula called the optimization equation, for which you are trying to find the highest or lowest value. These four cases are as follows. First, infeasibility. In the final tableau, if one or more artificial variables, in order to use the simplex method or problems with mixed constraint, we turn to a device called an artificial variable. This variable has no physical meaning in the original problem and is introduced specially to find a basic feasible solution so that we can use the simplex method A1, A2 and so on. Still basic and has a non-zero value, then the problem has an infeasible solution. Second, unbounded solutions. When determining the leaving variable of any tableau, if there is no positive ratio, all the entries in the pivot column are negative and zeros, then the solution is unbounded. Third, degeneracy. A solution that has basic variable with zero value is called a degenerate solution. Fourth, multiple optimal solution. If there is a zero under one or more non-basic variables in the last tableau, optimal solution tableau, then there is a multiple optimal solution.
After studying this module, you shall be able to learn the special cases of LPP, recognize when a LPP has these special cases of solutions. Let us first understand infeasibility. Infeasibility happens when there is no solution that meets all of the problem's constraints. In the simplex method, an infeasible solution is specified by looking at the final tableau. All Cj minus Zj row entries will be of proper sign to infer optimality, but an artificial variable will still be in the solution mix. A situation with no feasible solution may exist if the problem was framed improperly. Also, infeasibility occurs when there is possible conflicting constraints. Indication of infeasibility. Even though all Cj minus Zj are positive or zero, the criterion for an optimal solution in a minimization case, an artificial variable remains in the solution mix. Or are negative or zero the criterion for an optimal solution in a maximization case, all non-slack variables are already in the basis. The feasible region is found to be empty, which indicates that the problem has no feasible solution. In terms of the ways of artificial variable techniques, the solution of optimality could include one or more artificial variables at a positive level, that is, as a non-zero basic variables. In such a case, matching constraint is violated and the artificial variable cannot be driven out of the basis. The feasible region is thus empty. Maximize x0 is equal to 2x1 plus x0 is equal to 2x1 plus x2 subject to minus x1 plus x2 is greater than or equal to 2, x1 plus x2 is less than or equal to 1, x1 x2 is greater than or equal to 0. Let us consider the following LP problem. Using a surplus variable x3, an artificial variable x4 and a slack variable x5, the augmented system is minus x1 plus x2 minus x3 plus x4 is equal to 2, x1 plus x2 plus x5 is equal to 1, x0 minus 2x1 minus x2 plus mx4 is equal to 0. Now the columns corresponding to x4 and x5 form an identity matrix. In the tableau we have the following. After elimination of m in the x4 column, we have the initial tableau. Since m is a very large number, minus 1 plus 2m is positive. Hence, all the entries in the x0 row are non-negative. Thus, we have reached an optimal point. However, we see that the artificial variable x4 is equal to 1, which is not 0. This implies that the solution just found is not a solution to the original problem. Indeed, the x that satisfies ax plus ix a equal to b with xa not equal to 0 is not a solution to ax equal to b. Figure 1 shows that the feasible region to the problem is empty. Next, we will understand unboundedness. Unboundedness defines linear programs that don't have finite solution. It occurs in maximization problems. For example, when a solution variable can be made infinitely large without violating a constraint. In the simplex method, the situation of unboundedness will be revealed prior to reaching the final tableau. The problem will be manifested when trying to decide which variable to remove from the solution mix. As seen earlier, the procedure is to divide each quantity column number by the corresponding pivot column number. First, the row with the smallest positive ratio is changed. Second, but if all the ratios are negative or undefined, it indicates that the problem is unbounded. This is an example where the feasible region and the optimal value of the objective function are unbounded. Consider the LPP. Maximize x0 is equal to 2x1 plus x2, subject to x1 minus x2 less than or equal to 10, 2x1 minus x2 less than or equal to 40, x1 x2 greater than or equal to 0. The initial tableau is shown as no positive ratio exists in x2 column. Hence, x2 can be increased without bound while maintaining feasibility. It is clear from the figure. The following is an example where the feasible region is unbounded yet the optimal value is bounded. Consider the LPP. Maximize x0 is equal to 6x1 minus 2x2, subject to 2x1 minus x2 is less than or equal to 2, x1 is less than or equal to 4, x1 x2 is greater than or equal to 0. The computation goes as follows is shown. Figure shows that the unbounded feasible region with unbounded optimal value any x1 x2 is equal to 1k for k being any positive number is a feasible solution. The notion of finding degenerate basic feasible solution in a LPP is identified as degeneracy. The degeneracy in a LPP may rise at the preliminary stage when at least one basic variable is 0 in the initial basic feasible solution. At any following iteration, when more than one basic variable is eligible to leave the basic and thus one or more variables becoming 0 in the next iteration, and the problem is said to degenerate. There is no assurance that the value of the objective function will improve, since the new solutions may remain degenerate. As a result, it is likely to repeat the same steps of simplex iterations infinitely without refining the solutions. This notion is known as cycling or circling. Rules to avoid cycling. First, split each element in the tied rows by the positive coefficients of the key column in that row. Second, compare the resulting ratios column by column, first in the identity and then in the body from left to right. Third, the row which first contains the smallest algebraic ratio contains the leaving variable. Let us consider the following LPP and look for degenerate basic solutions are basic solutions with one or more basic variables at zero level. Also for degeneracy that occurs when one or more of the constraints are redundant. Maximize x0 is equal to 2x1 plus x2, subject to 4x1 plus 3x2 less than or equal to 12, 4x1 plus x2 less than or equal to 8, 4x1 minus x2 less than or equal to 8, x1 and x2 greater than or equal to 0. When the objective function is parallel to one of the constraints, the multiple optimal solution may exist. After attaining optimality, if at least one of the non-basic variables holds a zero value in gradient j, the multiple optimal solution exists. Zero reduced cost coefficients for non-basic variables at optimality indicate alternative optimal solutions, since if we pivot in those columns, x0 values remains the same after a change of basis for a different BFS. Notice that simplex method yields only the extreme point optimal BFS solutions. Usually, the set of alternative optimal solutions is given by the convex combinations of optimal extreme point solutions. Figure shows infinitely many optimal solutions. Any x1, x2 which is equal to 1k for k being any positive number is a feasible solution. Consider maximize x0 equal to 4x1 plus 14x2, subject to 2x1 plus 7x2 less than or equal to 21, 7x1 plus 2x2 less than or equal to 21, x1 or x2 greater than or equal to 0. Thus, all convex combinations of the points 0, 3, 0, 15 and 7 by 3, 7 by 3, 0, 0 are optimal feasible solutions.
Let us now summarize what we have learned in this module. First, infeasibility. This occurs when final tableau has one or more artificial variables still basic and has a non-zero value. Second, unbounded solution is a solution when the leaving variable of any tableau is determined if there is no positive ratio. All the entries in the pivot column are negative and zeros. Third, degeneracy is a solution that has a basic variable with zero value. Fourth, multiple optimal solutions. This occurs when there is a zero under one or more non-basic variables in the last tableau.